Happy to be back in another episode of Environmental Digest. And today, we are going to talk about the complex environmental trade-offs of next-generation water purification systems.
Yeah, it's a really crucial deep dive. We're looking at a classic problem. The need for clean water is slamming right up against the need for, sustainability.
And today, we are really zeroing in. Our mission is to figure out the true environmental footprint of a new technology called electrified membrane, or EM for short.
We're using a full cradle-to-grave life cycle assessment, an LCA, and we're benchmarking this new EM tech against the current standard.
Which is sequential ultrafiltration, nanofiltration, UFNF.
Exactly. And we're being really specific with our comparison. The goal, the functional unit, is the removal of just 1 gram of perfluorooctanoic acid, PFOA.
Oh, PFOA. One of the infamous forever chemicals.
That's the one, part of the PFAS family. It's incredibly stable, toxic, resists any kind of natural breakdown. It's a huge challenge for water systems everywhere.
So the stakes are high. And the reason this matters so much is scale, right? Water utilities are just massive energy hogs.
Oh, absolutely massive. Globally, they use something like 1.2 to 2.7% of all electricity generated. It's a staggering number.
Which is why everyone's pushing for these decentralized, more efficient systems.
So let's talk about the two contenders. First, the benchmark, UFNF. We know it works for PFOA removal, but what's the catch?
The catch is energy. It's a high-pressure system.
Very high-pressure system. Yeah. You need these huge pumps to force water through the membranes. That means high energy use, somewhere between 2.5 and 4.0 kilowatt hours per cubic meter.
And it's not just the energy, is it? It also produces this toxic sludge.
Exactly. It creates a concentrated brine full of the PFOA you just filtered out, and that waste needs its own, secondary treatment. It's another hidden cost, another environmental burden.
Okay, so that's the old guard. Now let's talk about the new challenger, electrified membranes. The promise here is, well, it's huge.
It is. The whole concept is built around low-pressure filtration combined with electrophenomena. So right away, the energy consumption for pumping just plummets. We're talking 0.01 to maybe 0.4 kilowatt hours per cubic meter.
Just a fraction of the old system.
And here's the really revolutionary part. The EM system uses an electric current to generate what are called reactive oxygen species, or ROS, right there inside the system.
In these ROS, they just attack the pollutants.
They essentially destroy them. They oxidize things like PFOA, breaking them down instead of just collecting them.
So low energy, no toxic sludge to deal with. I mean, on paper, that sounds like a complete win, the silver bullet we've been looking for.
It really, really should be. But, and this is the entire reason for this deep dive, there's a critical knowledge gap. Does the EM system's need for extra electricity to make those ROS and some chemicals called electrolytes, does that completely wipe out all those amazing energy savings?
Okay, let's unpack this then. Let's get to the data.
When you look at the current lab scale tech, the results are, well, they're shocking.
Shocking is a good word for it. It really flips the whole script.
It does. The core finding is that this new EM technology actually has a significantly higher total greenhouse gas emission rate than the old UFNF system.
Can we put some numbers on that? I think hearing them side by side is important.
Okay. To remove that 1 gram of PFOA, the conventional UFNF system comes in at 8.60 kilograms of CO2 equivalent.
8.60 kilograms, okay. And the new, supposedly greener EM tech?
19.70 kilograms of CO2 equivalent.
Wow. That's more than double.
More than double. I mean, for a technology that's meant to be an improvement, that's a massive failure right out of the gate. It forces you to ask, where is all that environmental cost hiding?
Good question. Before we dig into EM's problems, let's quickly break down where the old system, UFNS, is spending its carbon budget.
Sure. For UFNF, the biggest single piece of the pie, surprisingly, is maintenance. That's 52.3% of its impact.
Wait, not the energy for the pumps. Maintenance.
Yeah. Maintenance. It's the constant need for cleaning chemicals, sodium hypochlorite, sodium hydroxide, acids. You have to keep flushing the system to keep those membranes working under high pressure.
So over half the environmental cost is just cleaning the machine.
Pretty much. The actual pumping is second at 33.4%, and then end-of-life impacts are about 14%. And that last part is really interesting in some specific categories.
Like marine eutrophication, which you mentioned. Can you just break that down for us? What is that in simple terms?
So eutrophication is basically over-fertilizing the water. too many nutrients like nitrogen and phosphorus. And in this case, the cleaning chemicals and the concentrated wastewater from the UFNF system are packed with them.
And that leads to things like algal blooms.
Exactly. Harmful algal blooms that suck all the oxygen out of the water and create dead zones. For UFNF, that wastewater problem at the end of its life accounts for over 80% of its total impact on marine eutrophication. It's a huge issue.
Okay, so UFNF is a messy, high-pressure, chemical-heavy process. Now back to EM, which was supposed to solve all that. We know its strengths are real.
Oh, they absolutely are. The pressure it needs is tiny, so pump electricity is almost nothing, less than 0.01 kilowatt hours per gram. And since it sort of self-cleans with those ROS, its maintenance and end-of-life emissions are also practically zero.
Sounds amazing. But you said all those benefits are completely wiped out by just one single stage of the process.
That's the unbelievable part, the electrofiltration operation stage. That one stage is responsible for 86.2% of EM's total greenhouse gas emissions.
86%.
Yeah.
So it's not the fancy membrane or the machine itself. It's what we're feeding it during operation.
Exactly. So we had to look inside that operational phase. And there are two main culprits, two environmental hotspots.
What's hotspot number one?
Hotspot number one, and this is the big one, the overwhelming driver, is the supporting electrolyte.
The chemical they add to the water to help the electricity flow better?
Precisely. In the baseline study, they used a chemical called potassium hydrogen phosphate, K2H-PO4. And that one additive, that single chemical, is responsible for 65.5% of the EM's entire carbon footprint.
Hold on. Two-thirds. Two-thirds of the carbon footprint comes from producing and transporting one chemical.
A staggering 12.81 kilograms of CO2 equivalent per gram of PFOA removed. It's just from that one chemical.
How is that possible? Why is the supply chain for that chemical so much worse than, running massive pumps?
Because this is where traditional engineering thinking can fail. We focus on the machine's energy use, the visible part. But the LCA forces us to look upstream. The huge emissions aren't at the water plant. They're in the mining, the chemical processing, the transport needed to make that high-purity chemical. It has a massive hidden energy cost.
We're swapping a visible energy cost for an invisible supply chain cost.
And the sensitivity analysis proves it. If you just decrease the concentration of that chemical by 10%, you immediately cut 1.29 kilograms of CO2 from the total. It's the biggest lever you can pull.
Okay, so that's the first 66% of the problem. What's hotspot number two?
Hotspot 2 is the electricity. Specifically, the power needed to generate those reactive oxygen species that destroy the PFOA. That accounts for another 20.7% of the total greenhouse gas emissions.
And I'm guessing that number is super sensitive to where you get your power.
Extremely. The study used a global average grid mix, which is still about 62% fossil fuels. If you build one of these plants in a region that relies heavily on coal, for instance, its environmental performance gets even worse.
So the fate of this technology is completely tied to two inputs: the chemical you put in it and the electricity you power it with. The fancy membrane is almost an afterthought in the carbon calculation.
Which points us directly to the solutions, the optimization strategies.
Let's start with strategy one then, electrolyte optimization. That's the biggest piece of the pie. The dream scenario would be to just get rid of it entirely, right?
Yeah, eliminating it gives you that maximum 66% reduction. But even short of that, the easiest, most practical step is just switch chemicals. The potassium phosphate they used was just a terrible choice from a carbon perspective.
So what's the alternative?
A much more common and much cleaner chemical, sodium sulfate, Na2SO4.
And carbon footprint is lower.
Dramatically lower. We're talking 0.27 kilograms of CO2 per kilogram of chemical compared to over 3 kilograms for the potassium phosphate. It's not even in the same league.
And I bet it's cheaper too.
Oh, vastly. Sodium sulfate costs around $45 a ton. The potassium phosphate, over $1,300 a ton.
So you get massive cost savings and massive environmental savings at the same time. It seems like a no-brainer. What does that one simple switch do to the EM's final carbon score?
Just switching to sodium sulfate at the same concentration cuts the EM's total greenhouse gas emissions by 55.3%.
55%. What does that bring the number down to?
It brings it down to 8.81 kilograms of CO2. All of a sudden, just by swapping one chemical, the new EM technology is right there, competitive with the old UFNF system's 8.6 year.
And from there, you can start to improve even more. What if you also lower the concentration?
Exactly. If you drop that sodium sulfate from 100 millimolar down to just 5 millimolar, The EM process starts to beat the old UFNF system in almost every single environmental category.
It really shows that your choice of input is everything.
It does. And this leads to a really interesting thought about where this tech could be used first.
You mean not for drinking water?
Potentially, not at first. Imagine you use it on certain types of industrial wastewater like saline waste or water from electroplating factories. That water is already full of ions, it's already highly conductive.
So you wouldn't need to add any extra electrolyte at all.
None. And you'd instantly realize that 66% reduction in greenhouse gases. It suggests the best first use for EM might be in these very specific niche industrial applications.
Okay, let's move to strategy 2, the electricity. That was the second hot spot. What happens if the grid gets just a little bit cleaner? Say, a 10% reduction in carbon intensity.
That gives you a noticeable cut of 0.65 kilograms of CO2 per gram for the EM process. Not as big as the chemical swap, but still very significant.
And what about the ideal scenario? The system is powered entirely by renewables, a dedicated solar farm or wind turbine.
In that case, you get a 33% reduction potential from the electricity alone. The total GHG emissions drop to an estimated 6.57 kilograms.
So now you're clearly outperforming the old UFNF benchmark of 8.60.
By a very healthy margin, yeah. It really shows that the future of clean water tech is completely tied to the future of the clean energy grid. They're linked.
So what happens when you combine everything? The absolute best case scenario.
Right. The study calls this the combined optimization. This is where you assume you need no extra electrolyte, you use clean energy for the degradation process, and you even use clean energy to manufacture the membrane itself.
And the results?
They are phenomenal. You get reductions between, let's see, 82 and 99% across all 17 environmental impact categories. Things like land use get cut by over 92%. It's the full realization of the technology's promise.
But it requires those two external factors to be perfect. A clean supply chain and clean energy.
It proves that optimizing the simple stuff, the chemicals and the electricity, is way more important than just focusing on making a slightly better membrane material.
So let's wrap this up. What does this all really mean? The primary takeaway seems to be that this electrified membrane technology, it's genuinely promising. Its core operation is efficient, low pressure, and it doesn't have the huge maintenance and chemical burden of the old systems.
But, and it's a huge but, its current environmental sustainability has almost nothing to do with the sophisticated membrane material. It all hinges on two very practical and often overlooked factors: the choice and amount of the supporting electrolyte, which was 66% of the problem, and the carbon intensity of the grid, which was the other 33%.
So the key takeaway for you, the person listening, is that when you look at any green technology, you have to look upstream. The future of EM isn't just about better materials science. It's about clever engineering to make it work with little or no chemical additives. And it's about plugging it into green energy.
Which brings us to a final provocative thought to leave you with. We've established that the technology is at its absolute best when it needs no extra electrolyte. This happens naturally in high-conductivity industrial wastewater. So does that mean EM's truly sustainable future is actually in those niche industrial applications? Is it a precision tool for industry rather than a scalable, general-purpose solution for treating our decentralized fresh water? That's the big question that remains.